Hello, everyone. My name is Eduardo Servin Fernandez. I hold a master's degree in engineering and applied sciences, and I am currently pursuing my doctorate in the same field. Today, I am pleased to present our research on the application of aluminum, chromium, copper, iron, nickel, and aluminum 15, silver 5, chromium, copper, iron, nickel, high entropy alloys as coatings on the steel substrates. In engineering, mechanical components suffer from accelerated wear and corrosion under harsh environments. To mitigate this damage, surface engineering offers high entropy alloys as an innovative solution. These multi-component systems consist of 5 or more elements in near equiatomic proportions, yielding outstanding properties. Our objective was to synthesize these advanced coatings using mechanical alloying, a highly cost-effective method compared to conventional industrial processes. Now let us break down the experimental process step by step, as illustrated in the main diagram of our poster. First, in the materials preparation stage, high-purity elemental metal powders were carefully weighed. We prepared 2 specific systems, a baseline aluminum, chromium, copper, iron, nickel alloy, and a silver-modified aluminum 15, silver 5, chromium, copper, iron, nickel alloy. As shown in the synthesis diagram, these mixtures were processed using mechanical alloying. The powders were loaded into a planetary ball mill running at 400 revolutions per minute under a protective argon atmosphere to prevent oxidation. We utilized a strict 5-to-1 ball-to-powder weight ratio. During this 40-hour milling process, the particles underwent continuous cycles of cold welding, fracturing, and rewelding due to the high energy impact between the balls and the powder, resulting in a refined nanostructured product. Next, look at the coatings schematic. These pre-alloyed HEA powders were successfully deposited onto machinery grade A ISI, tin 45 and 4140 steel substrates. This second deposition stage was carried out using mechanical alloying for up to 12 hours at 400 revolutions per minute under argon, adjusting the ball-to-powder ratio to 10-to-1. Finally, to ensure proper densification, structural stability, and a strong metallurgical bonding with the substrate, the developed coatings underwent a vital post-deposition sintering thermal treatment. Afterwards, the functional properties of these sintered coatings were thoroughly characterized using X-ray diffraction, scanning electron microscopy, micro-hardness testing, and electrochemical corrosion assays. Let's dive into the results, beginning with the characterization of the synthesized high-entropy alloys in powder form. If you look at the X-ray diffraction patterns on the left, we can trace the structural evolution from 0 to 40 hours of milling. As milling time increases, the sharp individual peaks of the elemental metals gradually disappear and broaden. This confirms the successful diffusion and transition into a nanostructured solid solution with the coexistence of BCC and FCC phases. This refinement is mathematically supported by the crystal size evolution plot, calculated via the Scherer equation. The crystal size drops drastically during the early stages of milling and stabilizes below 6 nanometers at 40 hours. Furthermore, scanning electron microscopy images in Figure 3 visually confirm this morphological evolution. We transition from the initially irregular, coarse elemental powder mixture at 0 hours into a highly homogeneous and refined particle structure after mechanical alloying. Now let us discuss the performance of these materials when applied as coatings. The X-ray diffraction patterns of the coatings confirm the structural stability of the main BCC and FCC phases. Crucially, the X-ray diffraction analysis reveals that the thermal energy from the post-deposition sintering process triggers the nucleation of a new, distinct silver-rich FCC phase. This phase separation is a unique feature of the sintered coating and does not occur in the mechanical alloyed high-entropy alloy powder form. Additionally, the formation of minor iron and chromium oxides contributes positively to the system's protective surface behavior. In terms of mechanical performance, the Vickers micro-hardness profiles demonstrate a massive improvement over the untreated steel substrates. The baseline aluminum, chromium, copper, iron, nickel coating increased the surface hardness of the 1045 steel by an outstanding 200%, while the silver-containing coating showed a 100% increase. The shaded area in Figure 5 delimits a uniform coating thickness of approximately 150 micrometers. Finally, the electrochemical evaluation in a 3.5 weight% sodium chloride solution highlights the benefit of silver modification. The potentiodynamic polarization curves exhibit a distinct shift toward nobler potentials and a significantly lower corrosion current density for the silver-modified coating. This superior protective capability is fully validated by the Nyquist diagrams from electrochemical impedance spectroscopy, where the larger semicircle diameter for the silver alloy confirms a much higher polarization resistance against aggressive saline environments. In conclusion, nanostructured high-entropy alloys were successfully synthesized after 40 hours of milling. Both coatings substantially enhanced the baseline hardness of industrial machinery steel. Furthermore, the addition of silver proved to be a critical factor in improving chemical stability against saline environments. Therefore, these developed high-entropy alloy systems represent highly effective and viable candidates for protecting structural steel components in severe marine or industrial conditions. Thank you very much for your attention.